High above Earth, thousands of silent machines still circle the planet's satellites whose signals faded long ago, yet whose orbits continue without anyone listening. Tonight, on Fall Asleep with Science, we drift toward these forgotten wanderers, ghost satellites that move through the dark with no mission, no contact, only momentum. Some were lost by accident. Some simply outlived their purpose. And now they form a quiet cemetery of technology, orbiting at thousands of miles per hour. There is something strangely peaceful about that human creation surviving only as silence. If this gentle curiosity helps you unwind, a soft like and quiet subscribe guide others here too. When you're ready, we'll follow their faint, invisible paths slowly, and together. Most of us are familiar with the International Space Station or the modern rovers currently exploring Mars. However, humanity has launched a vast number of missions over the decades, utilizing trailblazers from various eras like Voyager, Venera, and Messenger. Quite a few of these machines are still out there. They are forgotten remnants from an earlier age of exploration, quietly orbiting Earth, tumbling through interstellar space, or frozen in the shadows of other worlds. These ghost satellites act as time capsules. They are drifting reminders of our initial steps into the unknown. To understand them, we must look at where they went, what they discovered, and why they remain significant even as they fade into the cold background of deep space. This story begins with the early footsteps of a superpower. When we think of the space race, we often imagine rockets launching, astronauts floating in orbit, and flags being planted on the moon. But long before those famous landings, there were smaller, quieter beginnings involving machines that carried no people and satellites that never returned. Many of the first Soviet satellites launched in the late 1950s and early 1960s are still in orbit today, drifting in silence. The history of artificial satellites began with Sputnik on October 4th, 1957. The Soviet Union launched a small, round metal object into orbit. It was roughly the size of a beach ball, and its primary function was to transmit a simple radio beep. That beep, however, was heard across the globe. It signaled that the Soviet Union had reached space first, and the Cold War had entered a new technological phase. Sputnik 1 operated for only 21 days before its batteries failed. A few months later, it fell back into the atmosphere and burned up, but it was quickly followed by Sputnik 2, which carried the first living creature into orbit, a dog named Laika. That satellite did not return. Its systems failed within hours, yet it remained in orbit for over 5 months before re-entering the atmosphere. Next came Sputnik 3, a much heavier scientific satellite equipped with instruments to study radiation and cosmic rays. This machine stayed in orbit much longer. For years, its metallic body quietly circled Earth long after it had stopped transmitting data. No one controlled it, and no one listened for its signals, but it remained a physical part of the sky. Throughout the late 1950s and 60s, the Soviet Union launched a continuous series of satellites under names like Cosmos, Vostok, Luna, and Molniya. Some were purely for scientific research, while others served military purposes such as testing radar, spying on Earth, or relaying communications. Most of these objects remained in low or medium Earth orbit. Once their missions concluded, they were simply left in space. The Cosmos program was particularly vast. The Soviet Union used this name as a blanket term for hundreds of different satellites, many of which were classified. Some were experimental platforms, while others were disguised weapons tests or early warning systems. Due to their secretive nature, the government did not even acknowledge many of these satellites at the time. They were launched under the cover of night, tracked by Western radar, and logged into military databases. There were also early lunar missions. These probes were designed to reach the moon, but not all of them succeeded. Some failed during launch and fell back to Earth, while others reached Earth orbit but could not generate enough speed to escape the planet's gravity. These failures became unintentional ghost satellites. They were machines built to travel far into space but ended up stranded just above our atmosphere. Without fuel or guidance systems to correct their path, they remained in low orbit, dead from the start. In 1960, the Soviet Union began launching Vostok spacecraft, the same model that would later carry cosmonauts like Yuri Gagarin. Before sending humans, engineers tested the system with unmanned versions. These test flights used full-size capsules, complete with life support systems and telemetry equipment. Some failed to reach the proper orbit, while others succeeded and were eventually recovered. A rarely discussed category of Soviet satellites involves the Rorsat program, or Radar Ocean Reconnaissance Satellites, launched between the 1960s and 1980s. These machines carried onboard nuclear reactors. Unlike most satellites that rely on solar panels, Rorsats needed significant, constant power to operate their heavy radar systems. After completing their missions, most of these satellites ejected their nuclear cores into higher, safer orbits. However, the rest of the satellite, including the main body and the radar equipment, remained in low Earth orbit. Many are still there today. They are considered some of the most dangerous ghost satellites because of the collision risks they pose and the radioactive materials they once carried. Some of the earliest Soviet communication satellites came from the Molniya program. These satellites followed a unique elliptical orbit designed to cover northern regions for long periods. This was crucial for a country with vast territory near the Arctic Circle. A Molniya satellite would climb high above the Earth and then drop down rapidly, repeating this long oval path over and over. Dozens of these satellites were launched. Tracking these old objects is difficult. Many were launched with little public documentation, and some had their orbital data classified. Others drifted slightly off course after launch or shifted during their operational lives. Over the decades, these ghost satellites have blended into the background debris of space. Modern radar systems, both civilian and military, attempt to identify and catalog them, but it is a slow process. Since these satellites no longer transmit signals, they must be located visually or by bouncing radar pulses off their surfaces, which requires time and precision. Amateur satellite watchers have played a significant role in rediscovering these lost objects. Using ground-based telescopes, radio receivers, and tracking software, they have identified dozens of old Soviet satellites still moving overhead. Some have even captured photographs of these metal relics as they pass silently across the night sky. The intense rivalry that launched these satellites has ended, but its physical legacy remains above us. The The Soviet Union raced to space to demonstrate power and ambition. In doing so, it left behind a fleet of machines that no longer serve a purpose and no longer respond to commands. Yet they endure. Among these relics is the story of Salyut 1, the first space station in history. Salyut 1 marked the beginning of a new type of mission, where humans would not just visit space for a few hours but would live there. Launched on April 19th, 1971, it represented a major step forward. However, the station's operational life was short, and its story ended in silence. The goal of Salyut 1 was to create a habitat where cosmonauts could stay for weeks. Conducting research and studying how the human body reacts to long-term weightlessness, the station was over 15 meters long and weighed more than 18 tons. From the outside, it resembled a long metal cylinder with solar panels extending from its sides. Inside, it contained work areas, sleeping quarters, and a small kitchen. It was cramped, but it was a functioning home. After the launch, the Soviet Space Agency prepared to send a crew. On April 22nd, 3 cosmonauts lifted off aboard Soyuz 10, intending to dock with the station. However, the mission did not go as planned. The docking mechanism failed. Although the crew reached the station and came close enough to touch it, they could not secure a lock. They had to return to Earth without ever entering. Success finally came with Soyuz 11, launched on June 6, 1971. The crew successfully docked with Salyut 1. They entered the station and became the first people in history to live aboard an orbital outpost. Over the next 23 days, they worked extensively, running medical experiments, observing Earth, and testing the station's systems. It was a significant milestone. However, the return trip ended in tragedy. On June 30th, 1971, the crew undocked and began their descent. During re-entry, a cabin vent valve opened prematurely, causing the capsule to lose pressure. All 3 men died silently in their seats. Ground control only realized what had happened after the capsule landed and recovery teams opened the hatch. They were the first, and remain the only, humans to die in space beyond Earth's atmosphere. After the loss of Soyuz 11, the Soviet Union did not send another crew to Salyut 1. The station remained in orbit for a few more months, drifting silently above the planet. It was intact but unused. Engineers attempted to maintain contact, but without a crew to manage the systems or perform maintenance, the station could not last. On October 11th, 1971, it was guided into a controlled re-entry. Most of the structure burned up in the atmosphere over the Pacific Ocean. The mission was over, and steps were taken to ensure it did not become a hazard. Although the station is gone, pieces of it may still lie on the ocean floor, while no large sections are circling Earth. Small fragments could have separated during launch or docking maneuvers. These pieces are too small to be tracked closely, but they remain part of the debris field around our planet. The design of Salyut 1 also survived. The blueprints were used to build more advanced stations like Salyut 6, Salyut 7, and eventually Mir. Even the International Space Station today uses concepts that began with that metal tube in 1971. such as modular parts and docking ports. The tragedy of Soyuz 11 also forced a redesign of the Soyuz capsules. Crews began wearing pressure suits during launch and re-entry, and valve systems were made safer. When we consider ghost satellites, we often picture robotic probes, but crewed missions also leave traces behind. Salyut 1 was only in space for 175 days and hosted only one crew. Yet it proved that humans could live and work in orbit. It is not as famous as later stations, but it stands as the first human home beyond Earth. Meanwhile, the United States was developing its own orbital outpost. Skylab was America's first space station, and for a brief time in the 1970s, it represented the height of NASA's ambitions in low Earth orbit. Skylab was significantly larger than the Soviet stations. It was a broad cylinder designed to allow astronauts to move freely inside, featuring windows, laboratory space, and even a shower. Launched on May 14th, 1973. Skylab was built using hardware from the Apollo program. The main structure was a converted Saturn V rocket stage that had been hollowed out and fitted with scientific equipment and living quarters. It was a clever way to repurpose lunar exploration tools into a floating laboratory. However, problems began immediately. Just 63 seconds after launch, the micrometeoroid shield, which also provided thermal protection, tore off due to air pressure and vibration. This accident ripped away one solar array and jammed the other one shut. Without power or shielding, the station began to overheat. Internal temperatures rose to dangerous levels, rendering the station unusable. 10 days later, a crew of 3 astronauts launched to save it. They brought tools and a makeshift sunshade, a large sheet of material they managed to stretch over the station's exterior. The repair worked. The shade blocked the sunlight, lowering the temperature, and power was restored. 3 different crews visited Skylab between 1973 and 1974. The final group lived aboard for 84 days, setting a new record for time and space. They conducted experiments in medicine, physics, and solar observation, capturing thousands of detailed images of the Sun and Earth. Skylab proved that extended missions were productive. However, the station's future was being determined by forces outside of human control. NASA had hoped to revisit Skylab in the early 1980s using the Space Shuttle, which was under development. Engineers believed the shuttle could boost Skylab into a higher orbit or even refurbish it. But the shuttle program faced years of delays. At the same time, Skylab's orbit was slowly decaying due to atmospheric drag. Then, the sun intervened. In the late 1970s, solar activity increased more than predicted. This output heated Earth's upper atmosphere, causing it to expand. The denser atmosphere created more drag on the station, pulling it down faster. NASA realized they could not reach Skylab in time. There were no rockets available to boost it, and the shuttle was not ready. The agency knew the station was going to fall. The only question remaining was when it would happen and where it would land. The space agency tracked Skylab's orbit for months, attempting to predict the exact moment of re-entry. They issued warnings and sent updates to governments worldwide, hoping the station would break up safely over the ocean. However, no one could pinpoint the location. On July 11th, 1979, Skylab finally re-entered Earth's atmosphere. The massive station began to disintegrate high above the Indian Ocean, scattering debris along a wide path that extended over parts of Western Australia. Some pieces burned up in the atmosphere, but others survived. Metal fragments, heavy tanks, and sections of the laboratory's frame rained down onto remote areas. Fortunately, no one was injured, but the incident became a major global news story. At the time, it was the largest uncontrolled re-entry of a human-made object. Locals found pieces of Skylab scattered across the desert. In a moment of humor, one Australian town even fined NASA $400 for littering. Souvenir hunters collected the debris, and some of those pieces remain in private collections or museums today. Although most of the station was destroyed, some parts likely still rest where they fell, weathered by time but not forgotten. The fall of Skylab highlighted the risks of placing large objects in space without long-term disposal plans. Unlike Salyut 1, which was guided into a controlled descent, Skylab had no propulsion system to steer itself. NASA learned crucial lessons from this event. Later missions, including the International Space Station, were designed with clear protocols for orbit control and safe deorbiting. But in the 1970s, these systems were still being developed. Skylab was not part of a long series. It had no successor or second version. It was a singular experiment to see how far America could go with the hardware left over from Apollo. When the space shuttle finally launched in 1981, Skylab was already gone. The two programs missed each other by just a couple of years. Skylab served as a bridge between eras, proving that humans could live and work in space for months. It taught engineers how to build large, habitable structures in orbit. And though it fell, it left behind a legacy of knowledge and caution. While Skylab burned in the atmosphere, other relics remained perfectly preserved in silence. On the lifeless surface of the moon, Soviet landers sit under a sky that never changes. These are the remnants of the Luna program, left behind more than half a century ago. They remain motionless and untouched, where no wind or rain will ever disturb them. The Luna program represented some of the earliest and most daring steps in space exploration. The Soviet Luna program began in the late 1950s, at the height of the Cold War competition with the United States. It was a major effort to reach and study the moon. While American missions were still preparing to orbit Earth, the Soviets were already launching probes designed to strike the lunar surface or, if possible, land softly. Most early attempts failed, but each failure provided scientists with critical data. Every mistake pushed the design forward. In 1959, Luna 2 became the first human-made object to reach the moon, impacting the surface and ending its mission in a cloud of dust. It was a hard crash, not a landing, but it made history. Just weeks later, Luna 3 flew past the moon and transmitted the first images of the far side, revealing areas never before seen from Earth. These early missions were short-lived, but they proved the moon was reachable. The true breakthrough came with Luna 9 in 1966. It became the first spacecraft in history to make a soft landing on the moon and transmit photos from the surface. Unlike previous crash probes, Luna 9 touched down gently, using retrorockets and airbags. Once settled, Its petals opened like a mechanical flower to reveal a camera. The images it sent showed a flat, dusty surface beneath a black sky. There were no hills and no movement. But for the first time, people on Earth could see the lunar landscape from ground level. Over the next decade, the Luna program launched dozens of landers. Luna 13 followed in 1966 with improved cameras and soil sensors. Later missions like Luna 16, 20, and 24 performed even more complex tasks. They drilled into the lunar ground, collected samples, and launched them back to Earth. These were fully automated robotic missions, controlled by early computers and remote programming. There were no astronauts and no voice contact, just quiet signals sent across nearly 400,000 kilometers of space. Unlike orbiters, these landers remain fixed in one spot. They sit exactly where they came to rest, slowly collecting dust. The moon has no atmosphere to wear them down and no weather to scatter their components. Their metal frames may be cracked from the extreme cold, and their solar panels have likely faded from decades of radiation. But otherwise, they are unchanged. They act as time capsules from a lost era of exploration. Some of these landers were remarkably advanced. Luna 17 and Luna 21 carried robotic rovers known as lunocods. These machines explored the surface using wheels, cameras, and remote control. Lunacod 1, which landed in 1970, was driven by operators on Earth in real time, moving across the moon and transmitting hundreds of images. It was the first rover to operate on another world. The Soviets achieved this without sending humans. Their robots worked silently across kilometers of unknown terrain. However, these missions did not last long. Most lunar landers functioned for days or weeks before falling silent. Power systems failed, electronics wore out, and temperatures dropped far below freezing during the lunar night, damaging sensitive components. Once a lander shut down, it never restarted. There were no maintenance crews or recovery plans. When contact was lost, it was lost forever. The final mission, Luna 24, landed in 1976. It returned a small core sample containing 170 grams of moon dust and rock. This marked the end of the Soviet lunar program. Focus shifted to Mars, Venus, and Earth's orbit, and no further lunar craft were sent. The landers already on the moon were simply left behind. Modern missions have occasionally photographed these old machines. NASA's Lunar Reconnaissance Orbiter has captured detailed images of the Luna landing sites. In some cases, the tracks of the Lunacod rovers are still visible, etched into the dust like trails left by an ancient traveler. Since the moon has no storms, every wheel print remains exactly as it was laid down decades ago. These photos are the only proof that the machines are still there. From Earth, they are too small to be seen, and their signals stopped long ago. But they remind us that before GPS, smartphones, or space shuttles, humans built machines and sent them to another world. The Soviets often launched without knowing the outcome, facing unknown terrain and using primitive software. Yet, they persisted. Each success was hard-won, and each failure was a lesson. There is a quiet dignity in these machines. They proved that robotic exploration was possible, even with limited technology. In a way, they are the ancestors of every rover on Mars and every probe exploring the solar system today. While the lunar landers sit in cold silence, another set of missions met a much more violent end. These are the Venera missions that melted on Venus. The surface of Venus is hot enough to melt lead. The air is thick with choking clouds of sulfuric acid, and the atmosphere is so heavy it crushes most machines. For decades, the planet remained nearly unreachable due to its hostility. Still, the Soviet Union tried. Repeatedly, they sent robotic probes to the second planet from the Sun. These were the Venera missions, bold attempts to land on a world that seemed designed to destroy them. The Venera program began in the early 1960s. Alongside Luna and Sputnik, Venus was chosen because it is Earth's closest planetary neighbor. From Earth, it shines brightly, but its beauty hides a deadly environment. Early Soviet scientists believed Venus might be similar to Earth, perhaps humid and cloud-covered. The first Venera probes never got close enough to confirm this. Many failed during launch or lost contact before leaving Earth's orbit. Others missed Venus entirely, but with each failure, engineers learned to strengthen structures and improve heat shields. In 1967, Venera 4 became the first probe to enter Venus's atmosphere and transmit data. Although it did not reach the surface, it revealed the truth. Venus was far more dangerous than expected. The air was mostly carbon dioxide. The clouds contained acid, and the surface pressure was 90 times that of Earth, comparable to being a kilometer underwater. Venera 4 was crushed mid-descent. Venera 5 and 6 followed, also failing to survive the journey down. Success finally came with Venera 7 in 1970. It was heavier, with a reinforced hull and a modified parachute designed to drop the probe faster, minimizing exposure to the heat. Venera 7 landed and survived for 23 minutes. It was the first spacecraft to transmit data from the surface of another planet. Its electronics eventually overheated, but it proved landing was possible. Subsequent missions pushed the limits further. Venera 8 lasted 50 minutes. Venera 9 and 10 sent back the first images of the surface blurry gray scenes of broken stones under a thick orange haze. The temperature was 470 degrees Celsius. Inside the probes, the heat-baked circuits and the pressure-squeezed frames. Cooling systems failed quickly, and internal parts warped. Each lander was designed to endure just long enough to send data before dying. Venera 13, launched in 1981, was one of the most successful, lasting over 2 hours. Its cameras showed a world coated in dust and rocks, tinted orange by the atmosphere. It also recorded sounds the first time humans heard audio from another planet. It captured the rush of wind and the mechanical noise of its own systems before silence returned. Venera 14 returned similar data, though its soil sampler failed after hitting its own ejected lens cap. Venera 15 and 16 remained in orbit, mapping the surface with radar. The landers, however, had no solar panels and no way to cool themselves indefinitely. Once they overheated, they shut down forever. Unlike the lunar landers, which sit intact, the Venera probes met a destructive end. Their circuits burned, wires melted, and hulls likely collapsed under the pressure. They are buried under the weight of the thick atmosphere, consumed by the world they touched. No mission has returned to see them, so their remains lie distorted and invisible beneath Venus's permanent veil. Their story is one of violence and endurance, paving the way for our understanding of extreme environments. They taught engineers how to design for heat and pressure, proving that survival, even for a brief moment, was possible. For now, the Veneralanders remain unreachable. These were ghosts forged in fire, the remains of a time when humans dared to reach down into a planet that burns. They were the first, and for now, still the only machines to transmit data from the surface of that hidden, violent world. While those probes melted on Venus, others were sent in the opposite direction, toward the cold expanse of the outer solar system. In the early 1970s, 2 small spacecraft were launched with a goal no machine had ever attempted before. These were Pioneer 10 and Pioneer 11. NASA's early scouts, Pioneer 10 launched first on March 2nd, 1972. Its mission was simple but ambitious: reach Jupiter, pass through its harsh radiation belts, and send back close-up images. Until then, Jupiter had been seen only through telescopes as a distant, cloudy mystery. Pioneer 10 made the journey in just under 2 years. On December 3rd, 1973, it flew past Jupiter at a distance of about 132,000 kilometers. It successfully transmitted detailed pictures of the planet's storms, moons, and magnetic field, surviving the intense radiation environment. With its primary job complete, Pioneer 10 continued on its path, pulled only by gravity and pushed by the momentum from its launch. It passed the orbit of Saturn, then Uranus, then Neptune. It traveled out of the plane of the solar system, heading in the direction of the constellation Taurus. It had no steering system and made no course corrections, simply continuing a quiet flight into darkness. Pioneer 11 followed a year later, launched on April 5th, 1973. It had a similar goal but a different trajectory. It flew by Jupiter in 1974, using the giant planet's gravity to bend its course towards Saturn, a maneuver never performed before. In September 1979, Pioneer 11 became the first human-made object to visit Saturn, flying just 21,000 kilometers above the cloud tops. It returned photos of the rings and confirmed the planet's strong magnetic field. Like its twin, Pioneer 11 was built to be tough but basic. Its instruments were designed in the 1960s, and its memory was measured in kilobits. Yet, after its planetary tour, it also departed for deep space. The farther they traveled, the fainter their signals became. NASA continued to track them for many years. Pioneer 10's signal was last received on January 23rd, 2003. At that time, it was more than 12 billion kilometers from Earth. The signal was incredibly weak, a mere whisper against the static of the universe. Taking over 11 hours to travel to Earth, Pioneer 11 stopped communicating earlier. With contact lost in 1995, it was heading toward the constellation Scutum when its power faded and its systems shut down. Today, Both Pioneers are still moving slowly and silently away from the Sun. They have passed the orbits of all known planets and are moving through the outer regions of the heliosphere. Beyond that lies interstellar space. It will take many thousands of years for them to reach distant stars, but they are drifting along paths set decades ago. Each spacecraft carries a small gold anodized aluminum plaque bolted to its frame. The plaque, designed by Carl Sagan and Frank Drake, with artwork by Linda Salzman Sagan, depicts a man and a woman to scale with the spacecraft. It also includes a map showing the position of Earth in relation to pulsars and a diagram of the solar system marking the Pioneer route. This is not a scientific tool. It is a greeting from a planet orbiting a small star, sent into the dark in case it is ever found. The odds of recovery are statistically impossible. As space is vast and the probes may never pass close to another star system, Pioneer 10 is heading toward the red dwarf star Ross 248. If it continues in a straight line, it will pass near that star in about 2 million years. However, it lacks the speed to escape the galaxy. Eventually, gravity will slow it, and it will begin a long, looping orbit around the Milky Way, remaining a silent passenger for billions of years. The spacecraft themselves are likely still intact. In the vacuum of space, there is no wind, water, or weather to cause erosion or rust. Their metal frames have likely cooled to near absolute zero. Inside, the wires and circuits are frozen in place. The radioactive power sources, once glowing with heat, have faded. The journey of these small machines outlasted every plan made for them. Building on the success of Pioneer, the Voyager program aimed even higher. In the summer of 1977, 2 spacecraft were launched to take advantage of a rare alignment of the outer planets that occurs only once every 176 years. Voyager 2 lifted off first, followed a few weeks later by Voyager 1. They carried instruments, cameras, and sensors to explore the giant planets. But they also utilized a technique called gravity assist. By flying past a planet, each spacecraft could steal a small amount of momentum from the planet's orbit to gain speed and change direction. Voyager 1 visited Jupiter and Saturn. Voyager 2 completed the full tour, visiting Jupiter, Saturn, Uranus, and Neptune. No spacecraft has replicated that journey since. They returned stunning data: volcanoes on Io, rings around Jupiter, storms on Saturn, and icy worlds at the edge of sunlight. Scientists learned about magnetic fields and atmospheric chemistry that had previously been theoretical. By 1990, the planetary missions were complete, but the Voyagers kept moving. As their instruments aged, engineers reconfigured them to conserve power. One by one, non-essential systems were turned off. Yet, they still send back data, caught by the giant antennas of the Deep Space Network on Earth. Today, Voyager 1 is the farthest human-made object in existence. In 2012, it crossed the boundary of the heliosphere and entered interstellar space, the region where the sun's influence gives way to the pressure of other stars. Voyager 2 followed in 2018. They are now travelers between stars. Voyager 1 is heading toward the constellation Ophiuchus, while Voyager 2 heads toward Sagittarius. It will take tens of thousands of years for either to approach another star. Their radioactive generators are slowly fading. By 2030, or shortly after, they will likely fall silent. However, the spacecraft will continue to drift, carrying a unique cargo. Attached to the side of each Voyager is a 12-inch gold-plated copper disc known as the Golden Record. The record is mounted beneath a protective aluminum cover that displays instructions on how to play it, along with a map of Earth's location. Inside, the disc contains 115 images, greetings in 55 languages, sounds of Earth, and 90 minutes of music. The audio includes a baby's cry, thunder, laughter, a heartbeat, and the sounds of animals and machinery. The music ranges from Bach and Beethoven to a Navajo chant, a Bulgarian folk song, and tracks from Senegal, Peru, and India. It was designed to represent not just human biology, but human feeling. Carl Sagan described it as a bottle cast into the cosmic ocean. A printed message from United States President Jimmy Carter was also included, stating that this was a present from a small, distant world, attempting to survive its time so it might live into another. There is no fuel left to adjust their course. The Deep Space Network must listen intently to hear them, as the signal strength is less than a whisper. A signal from Voyager 1 now takes over 22 hours to reach Earth. Yet, that faint signal carries data about cosmic rays and the plasma of interstellar space. When they were launched, they carried computers with less processing power than a modern pocket calculator. Yet they have outlived almost every machine of their era. In time, micrometeorites may pit their surfaces, and cosmic radiation may erode the data, but they will keep moving for millions of years. If another civilization ever finds the Golden Record, they will hold a snapshot of Earth as it was in 1977. Not all satellites leave the solar system or decay in Earth orbit. Some are repurposed for entirely new missions. The International Cometary Explorer, launched in 1978, is one such example. Originally named ISE-3, or the International Sun-Earth Explorer 3, it was part of a trio sent to monitor the solar wind. It was positioned at the L1 Lagrange point, about 1.6 million kilometers from Earth towards the Sun. At this location, the gravity of the Earth and the Sun balance perfectly, allowing the satellite to hover in a stable position. For years, it monitored how charged particles from the Sun interacted with Earth's magnetic field. By the early 1980s, the spacecraft had exceeded its lifespan. Instead of retiring it, engineers realized it could be used for something bolder, an encounter with a comet. This required a complex series of maneuvers. Engineers used the moon's gravity to sling the spacecraft out of its stable orbit and onto a new path around the Sun. In 1983, it was renamed the International Cometary Explorer, or ICE. This marked a rare shift in purpose for an active satellite. ICE was targeted at Comet Giacobini-Zinner. This comet was not as famous as Halley's Comet, but its orbit was reachable. On September 11th, 1985, ICE flew directly through the tail of the comet, becoming the first spacecraft in history to do so. The encounter with Comet Giacobini-Zinner provided scientists with critical data on the structure of a comet's tail, its interaction with the solar wind, and the speed of particles within it, ICE survived the crossing, remaining operational after years in space and a journey far beyond its original design. Following this success, the spacecraft continued its voyage. In 1986, ICE passed near Halley's Comet. Although it did not approach as closely as other probes like ESA's Giotto, it provided essential support from a distance, measuring the solar wind to help scientists understand the shape of Halley's tail. Over time, ICE drifted farther from Earth. Its instruments continued to function, even though no further comet missions were planned. Eventually, in 1997, NASA officially ended contact. However, the spacecraft was not dead. For years, it floated quietly through space, a retired worker that had outlasted every project, remaining on its own solitary path. Then, in 2014, something unusual occurred. A group of citizen scientists and engineers, calling themselves the ISEE-3 Reboot Project, decided to attempt contact. They knew ICE's orbit would bring it close to Earth again for the first time in decades. Using crowd-funded resources, they analyzed old mission data, studied the communication protocols, and obtained permission from NASA to try. Since the original equipment from the 1980s no longer existed, the team utilized the massive dish antenna at the Arecibo Observatory in Puerto Rico to send a signal. To everyone's surprise, ICE responded. After 36 years, the spacecraft was still listening. The project hoped to redirect ICE into a new orbit and return it to scientific duty, perhaps measuring solar wind or monitoring space weather. However, time had taken its toll. When the team attempted to fire the thrusters, the results were inconclusive. Analysis suggested that the nitrogen pressurant required to push fuel to the engines had leaked away. Without it, the thrusters could not fire. ICE had the will to continue, but not the physical capability. Despite this, the attempt brought renewed attention to a long-forgotten mission. For a brief moment, ICE spoke again. The team collected whatever data they could, listened to the final transmissions, and watched as the spacecraft moved on. With no fuel to maneuver, ICE passed Earth and headed away once more, continuing on a heliocentric orbit that may last for centuries. The story of ICE differs from that of Voyager or Pioneer. It began with its gaze fixed inward toward the sun, then turned outward toward a comet. It crossed disciplines from heliophysics to planetary science and adapted mid-mission. Its transformation was not planned at launch, but was an opportunity seized by minds on the ground. ICE was not a headline name. It carried no golden record and returned no dramatic images. Most people have never heard of it. Yet, it was the first spacecraft to fly through a comet's tail, the first to orbit a Lagrange point, and the first to be revived by citizens rather than a space agency. Now, it is one of the quiet objects drifting through the solar system, still in orbit, still whole, but invisible. Somewhere not too far from Earth, ICE circles the sun. Its solar panels still face the light, but the current has nowhere to go. Its instruments are powered down. Its mission is over. It belongs to a group of machines that tell a story not just of exploration, but of persistence. While some missions survive against the odds, others fall silent before they can begin. Mars, now a familiar destination for rovers and orbiters, was once a graveyard for early space ambitions. Long before helicopters took flight in the thin Martian air, many spacecraft died quiet deaths trying to make contact. They were the first wave, and most never called home. The history of failed Mars missions stretches back to the dawn of space exploration. The Soviet Union was the first to attempt the journey. In the 1960s and 70s, they launched a series of probes under the Mars program. These machines were built with the technology of their time, large, heavy, and complex. But Mars is a difficult target. Reaching it is hard. Landing is harder. And communicating afterward is the hardest part of all. Mars 1, launched in 1962, was one of the very first interplanetary missions. It successfully left Earth's orbit, but communication was lost after about 100 million kilometers. The probe continued flying, but never sent another signal. Engineers believed a leak in the orientation gas lines caused the failure. The spacecraft is still out there, silently circling the sun. Mars 2 and Mars 3 launched in 1971 with high expectations. Each mission included an orbiter and a lander. Mars 2's lander was released too early during descent. It entered the atmosphere at a steep angle and crashed. No data was ever received. Mars 3's lander, however, touched down successfully. For a moment, it made history as the first spacecraft to soft land on Mars. But the triumph was brief. The signal lasted only 14.5 seconds before cutting out. The cause remains unknown. Perhaps a fierce dust storm, equipment failure, or both. For decades, the landing site was lost. In 2013, amateur researchers using high-resolution images from NASA's Mars Reconnaissance Orbiter believed they spotted the remnants, a parachute, a heat shield, and the lander itself. Yet, Mars 3's silence remains. It touched the planet and died in the same breath. Subsequent Soviet attempts also faced difficulties. Mars 4 missed its orbital insertion and flew past the planet. Mars 5 achieved orbit but failed after a few days. Mars 6 released a lander that transmitted data during descent but ceased responding upon impact. Mars 7's lander never entered the atmosphere due to a release system failure, drifting past the planet into space. All these missions ended in silence, leaving pieces that may still lie on the Martian surface, preserved in dust. The United States also struggled. Before the success of Viking, there was the Mariner program. Mariner 3 failed to escape Earth's orbit due to a faulty shroud. Mariner 8 crashed into the Atlantic Ocean, while Mariner 9 succeeded in orbiting Mars. Later missions faced new challenges. The Mars Observer, launched in 1992, was designed to study the Martian surface and climate. Just days before entering orbit, it went silent, likely due to a fuel tank rupture. It was lost without ever reaching its target. In 1999, NASA launched the Mars Climate Orbiter. It was intended to relay communications and gather atmospheric data, but it burned up in the Martian atmosphere due to a navigation error. One engineering team used metric units, while another used imperial. Later that year, the Mars Polar Lander vanished just before touchdown. Investigations suggested it shut off its engines too early, mistaking vibrations for landing, and crashed. Two small probes attached to it, called Deep Space 2, also failed to signal. India's Mars Orbiter mission, launched in 2013, was a major achievement as the first Asian spacecraft to reach Mars. However, contact was lost in 2022, likely due to fuel exhaustion during a solar eclipse. These silent missions taught engineers that Mars demands precision and punishes overconfidence. Today's successes stand on the foundation of these earlier failures. Two missions, in particular, symbolize the curse of the Red Planet, Beagle 2 and Schiaparelli. Beagle 2 was a British lander carried by the European Space Agency's Mars Express mission. Small and light, it was designed to search for signs of life in the Ascites Planitia region. It was scheduled to land on Christmas Day, 2003. Ground stations listened, but no signal came. For over a decade, its fate was a mystery. In January 2015, the Mars Reconnaissance Orbiter spotted unusual objects on the surface. Analysis confirmed them to be Beagle 2. The lander had touched down successfully and survived descent, but it had failed to fully deploy. It was shaped like a clamshell, and one of its solar panels had not opened, blocking the antenna. Beagle 2 had been sitting there, intact but mute, for 11 years. A similar story unfolded with Schiaparelli in 2016, part of the ExoMars mission. This demonstration lander separated from the trace gas orbiter and began its descent. It entered the atmosphere and deployed its parachute, but contact was lost just before landing. Telemetry revealed that a sensor error caused the lander to miscalculate its altitude, thinking it was below ground level. It cut its parachute and engines too early, falling freely and crashing at high speed. Beagle 2 and Schiaparelli remain on Mars, just beneath the dust or exposed to the sun. They are quiet reminders of the risks of exploration. Each carries the work and hopes of thousands, proving that even with modern technology, a safe landing is never guaranteed. They are joined now by active rovers and helicopters, but they remain part of the planet's history, the silent partners in our exploration of the Red Planet. The path to success on Mars was paved by these early sacrifices. The Red Planet did not welcome visitors easily, but every lander that fell short made the route for the next one just a little clearer. While Mars accumulated its silent sentinels, another mission headed inward, toward the blinding glare of the sun. This was Messenger, the first Mercury orbiter, now crushed in silence. Mercury is a place that barely feels real. It is the closest planet to the sun, a scorched world of extremes. One side can reach 420 degrees Celsius, while the other plunges far below freezing. It has no substantial atmosphere. It is small, dense, and heavily battered by solar radiation, reflecting sunlight like a metal plate left in the desert. For most of history, it remained largely unknown, too hard to study from Earth, too close to the sun for telescopes, and too difficult to reach with spacecraft. Then came Messenger, launched by NASA in 2004. The name was an acronym for Mercury Surface. space environment, geochemistry, and ranging. It was the first spacecraft ever designed to orbit Mercury. Before that, the only visit had been a quick flyby by Mariner 10 in the 1970s, which had mapped only about 45% of the surface. After that brief encounter, the planet returned to silence for 3 decades. Reaching Mercury is harder than it seems. Most deep space missions aim outward, away from the sun's gravity. Mercury lies inward, falling toward the massive gravitational pull of our star. To slow down enough to enter orbit, a spacecraft must shed a tremendous amount of speed. This requires time and precise trajectory design. Messenger took 7 years and utilized 6 planetary flybys, 1 of Earth, 2 of Venus, and 3 of Mercury itself before finally settling into orbit in March 2011. This long, winding route used gravity assists to brake the spacecraft, as traditional chemical engines could not do the job alone. Once in orbit, Messenger circled the planet every 12 hours. Its instruments scanned the surface, measured the magnetic field, and studied the thin exosphere. The photos it returned were stark, revealing a surface pockmarked with impact scars. But they also showed bright spots, strange hollows, and ancient ridges. Mercury proved to be far more geologically active than expected. Some surface features appeared to have formed relatively recently, within the last few million years. One of the biggest surprises was ice. Mercury's axis is tilted almost perfectly upright, meaning the floors of deep craters near the poles never see sunlight. In these permanently shadowed pockets, Messenger found radar-bright regions consistent with water ice. The idea of ice existing on the planet closest to the sun seemed impossible. Yet there it was, locked in eternal shadow, protected from the heat by geography alone. Messenger also helped solve the mystery of Mercury's density. The planet has a massive iron core, much larger than expected for its size. One theory suggested that a huge collision early in its history stripped away much of its crust, leaving behind a metal-rich remnant. Messenger's data supported this violent past. It also revealed that the surface was low in volatile elements like potassium and sulfur, further pointing to a history of intense heat. The spacecraft also studied the environment surrounding the planet. Mercury possesses a weak but active magnetic field. Messenger measured how solar wind particles interacted with this field, creating waves and disturbances. Unlike Earth's magnetosphere, Mercury's is constantly compressed and pushed around by the sun. It is a chaotic environment where the spacecraft captured bursts of fast-moving plasma and magnetic reconnection events, tiny explosions in space that flip magnetic fields and fling charged particles at high speeds. Over 4 years, Messenger completed more than 4,000 orbits, sending back hundreds of thousands of images. But eventually, it began to run out of fuel. Without propellant, it could not fight against the solar tide. Mercury's gravity and the pressure of solar radiation slowly dragged the spacecraft lower. The team extended its life with clever maneuvers, even using helium gas originally meant to pressurize fuel tanks to eke out the final adjustments. But by early 2015, the end was inevitable. On April 30th, 2015, Messenger struck the surface of Mercury at over 14,000 kilometers per hour. It left a small crater in the northern hemisphere, near a ridge called the Shakespeare Basin. No one saw the crash. The signal simply stopped. It was a planned descent, and engineers used the final days to perform ultra-low passes, gathering high-resolution data until the very end. Messenger was the first mission to orbit Mercury, and it made its discoveries alone. It had no fleet of satellites or landers for support. Its crash marked the conclusion of a mission that had lasted twice as long as planned. Now, there is nothing at Mercury. No active mission scans the surface. No signals return to Earth. The only trace of humanity is a fresh crater and the massive dataset left behind. A new mission, Bepi Colombo, is en route and will arrive in 2026. Until then, Mercury remains in silence, while Messenger burned in the inner solar system. Another spacecraft was navigating the asteroid belt. This was Dawn, exploring the fading light between Ceres and Vesta. Dawn launched on September 27th, 2007, from Cape Canaveral. Most spacecraft target a single body, but Dawn's mission was to explore two worlds, Vesta and Ceres. These were not ordinary asteroids. They were large, complex protoplanets that held clues to the early solar system. Dawn was designed to orbit both, becoming the first spacecraft to orbit two extraterrestrial bodies in a single mission. Vesta was the first stop. Dawn arrived in July 2011 after nearly 4 years of flight. To get there, it used ion propulsion, a technology that moves a spacecraft using a gentle, steady stream of electrically charged particles. It is slow but incredibly efficient. Instead of burning fuel in a quick burst, an ion engine pushes for months or years, allowing for complex maneuvers that chemical rockets cannot achieve. This flexibility allowed Dawn to orbit Vesta, leave, and then travel to Ceres. Vesta appeared as a battered relic. It was lopsided, marked by a massive impact basin near its south pole called Rhea Silvia. This crater is roughly 500 kilometers wide, nearly the width of Vesta itself. The impact that created it likely ejected debris that became the meteorites we find on Earth today. Dawn revealed a world of sharp ridges, ancient lava flows, and strange troughs. It was a dry, differentiated body with a crust, mantle, and core, a planet that never finished forming. After studying Vesta for over a year, Dawn spiraled away towards Ceres, the largest object in the asteroid belt and the only dwarf planet in the inner solar system. Ceres is different from Vesta in nearly every way. It is rounder, darker, less dense, and rich in water-bearing minerals. Dawn arrived in March 2015. As it settled into orbit, it revealed bright clusters inside craters. The most famous, located in Okator Crater, turned out to be sodium carbonate, a salt left behind by evaporating water. This suggested that Ceres once held liquid brine underground and might still be geologically active. Dawn also spotted cryovolcanoes, cold volcanoes that erupt water or mud instead of lava. One such feature, Ohuna Mons, rises over 4 kilometers above the surface. It stands as a smooth, lonely mountain on a world of craters, hinting that Ceres is not dead rock, but a complex, evolving world. Dawn orbited Ceres for years, changing altitude to map every ridge and basin. However, the spacecraft faced a critical issue. The hydrazine fuel used to power its orientation wheels was running out. Without it, Dawn could not point its antenna toward Earth or its solar panels toward the sun. By late 2018, the reserves were exhausted. On October 31st, Dawn missed a scheduled communication. The next day, it missed another. The spacecraft had powered down, unable to orient itself. Dawn remains in a stable orbit around Ceres. Unlike Messenger, it was not crashed into the surface. NASA chose to leave it in orbit to protect the dwarf planet from contamination. As Ceres may harbor organic compounds or water ice, today, Dawn circles quietly, a dead machine above a cold world. It bridged the gap between planetary science and asteroid studies, showing that these small bodies are not just debris, but survivors from the dawn of the solar system. Farther out, another mission ended with a poetic reunion. Rosetta launched in March 2004 with a singular goal: to catch a comet, fly alongside it, and land a probe on its surface. The target was Comet 67P, Churyumov-Gerasimenko, a dark, icy body on a 6.5-year loop around the sun. The chase took over a decade. Rosetta used gravity assists from Earth and Mars to gain speed. In June 2011, with no more planets to push it, the spacecraft entered deep space hibernation. For 31 months, it slept to save power. On January 20th, 2014, it woke up. Its target was ahead. As Rosetta closed in, images revealed the comet's strange shape: two lumpy lobes connected by a neck, resembling a rubber duck. It was about 4 kilometers across, charcoal dark, and covered in cliffs and pits. By August 2014, Rosetta entered orbit, navigating through the gas and dust venting from the comet's active surface. 3 months later, the lander Philae detached. It was designed to anchor itself to the comet using harpoons and ice screws. However, upon touchdown, the harpoons failed to fire. In the low gravity, Philae bounced, drifting across the surface for nearly 2 hours before settling in a shadowy crack. Its solar panels were blocked from the sun. Philae operated on battery power for about 60 hours, sending back valuable data on the surface composition before falling silent. Rosetta continued alone for 2 more years. It watched the comet wake up as it approached the sun, spewing jets of gas and dust, and then quiet down as it retreated into the cold. As the comet moved away from the sun, Rosetta's solar power began to dwindle. The mission team decided not to let the spacecraft die drifting. Instead, they planned a controlled descent. On September 30th, 2016, Rosetta slowly spiraled down to the surface of Comet 67P. It kept its instruments running, capturing images of dust, grains, and boulders until the very last moment. Its final transmission came from just meters above the ground. Then, contact was lost. Rosetta had joined the comet. It landed gently, likely buried in dust over time. No other spacecraft has ended this way, resting on the object it studied, traveling with it through the dark. And somewhere nearby, slowly decaying, is the orbiter that brought it there. While some missions end quietly, others finish in fire, scattering their remains like Hayabusa's ashes in the atmosphere. When Hayabusa launched in May 2003, it carried the hope that a small spacecraft from Earth could chase down a fast-moving object in deep space, land on it, collect samples, and return them safely. This had never been done before. Developed by JAXA, the Japan Aerospace Exploration Agency, the spacecraft was light and compact. It carried ion engines, sampling equipment, and a tiny lander named Minerva. Its target was a near-Earth asteroid called Itokawa, a small, potato-shaped stony body just over 500 meters long. Hayabusa had to travel over 2 billion kilometers to intercept the asteroid, reaching it in mid-2005. The journey was plagued by technical failures. Solar panels delivered less power than expected due to damage, and one of the reaction wheels used for orientation stopped working. Still, Hayabusa pressed on. When it finally arrived, it became the first spacecraft to orbit and attempt to land on such a small body. However, Itokawa was not a solid rock. It was a loose pile of rubble grains, pebbles, and boulders held together loosely by gravity. The mission faced immediate complications. The Minerva lander was deployed, but due to a timing error, it drifted off into space and was lost, never touching the surface. Then came the sampling attempt. Hayabusa tried to descend, contact the surface, fire a small projectile to kick up dust, and collect it. The first attempt failed when the projectile did not fire. A second attempt was made, but onboard glitches meant telemetry was incomplete. It was unclear if any sample had been collected. By this time, the spacecraft was damaged, and more reaction wheels had failed. As it prepared to depart, a fuel leak caused it to lose orientation, and communication was lost for weeks. Many feared the mission was over. However, the team slowly re-established contact and regained limited control. Despite its crippled state, Hayabusa began the long journey home, limping back using its ion engines to correct its course little by little. In June 2010, the mission reached its climax. The spacecraft released its sample return capsule, aiming it at the Woomera test range in Australia. The capsule plunged into the atmosphere, trailing a brilliant fireball, slowed by a heat shield and parachute. It landed safely in the desert. Hayabusa itself did not survive. It disintegrated in the atmosphere, burning up like a shooting star. When scientists opened the recovered capsule, they were cautious. At first, it seemed empty, but careful inspection revealed tiny grains, some less than a millimeter across. They were real pieces of Itokawa. Despite all the failures, Hayabusa had succeeded, becoming the first mission to return samples from an asteroid. But the story did not end there. Before launch, engineers had built duplicate hardware and backup modules. This is common practice for space missions to allow for testing and troubleshooting. In Hayabusa's case, one of these nearly complete engineering models became the basis for a new mission, Hayabusa 2. Using lessons learned from the first mission, engineers improved the design. Hayabusa 2 featured upgraded thrusters, more robust sampling tools, and better navigation. It launched in 2014, bound for a different asteroid, Ryugu. In 2018, it arrived and deployed multiple landers, including 2 rovers that hopped across the surface. It successfully collected 2 samples, even using a small explosive device to expose subsurface material. In 2020, Hayabusa 2 returned to Earth, releasing its capsule over Australia, unlike its predecessor. However, the main spacecraft had fuel remaining. Instead of burning up, it performed a flyby maneuver and continued into deep space. It is now traveling toward a new target, a small asteroid named 1998 KY-26, which it will reach in the 2030s, back on Earth. The capsule contained over 5 grams of material, far more than the first mission. These grains from Ryugu are now being studied for clues about organic molecules and water in the early solar system. While the original Hayabusa ended as ash, its rebuilt clone drifts onward. It proves that even hardware left behind can find a second life. Most missions are the only version of themselves, but Hayabusa's legacy lives on in the tools and spares that were given a new purpose. Another mission, Genesis, left a different kind of mark. Launched by NASA in August 2001, its goal was to collect particles of the solar wind and bring them back to Earth. To do this, Genesis traveled to the L1 Lagrange point, a gravitationally stable zone between Earth and the Sun, far from our planet's atmosphere. For over 2 years, from 2001 to 2004, Genesis remained at L1, collecting particles. It used arrays made of ultra-pure silicon, gold, sapphire, and diamond-like materials. These fragile panels trapped ions from the solar wind, building up a measurable sample over time. The purity of the materials ensured that scientists could analyze the solar wind without contamination. Once the collection was complete, the capsule began its return. Re-entry was scheduled for September 2004. The plan involved a mid-air capture. A parachute would deploy, and a helicopter would snag the capsule before it hit the ground. This was necessary because the delicate collector panels would shatter upon a hard landing. The capsule entered the atmosphere as planned, but the parachute never opened. A sensor designed to detect deceleration had been installed backward, fooling the system into thinking the capsule was still in space. It fell freely, slamming into the Utah desert at nearly 320 kilometers per hour. The impact destroyed the internal structure and shattered the collector panels into thousands of shards. Dust, glass, and soil sprayed across the desert floor. What should have been a gentle return became a crash site. However, recovery teams moved quickly, setting up clean rooms in the field to salvage what they could. They searched for fragments and even dust that might still hold traces of the solar wind. Remarkably, not all was lost. Scientists developed new techniques to clean the debris and isolate the solar particles. Genesis managed to provide some of the most pristine samples of solar wind ever studied. The data confirmed that the Sun has a different isotopic composition of oxygen and nitrogen compared to Earth, suggesting that the planets formed from material that had been altered from the original solar nebula. While the capsule crashed, another part of Genesis remains in space. The main spacecraft bus, which housed power and communication systems, did not re-enter. After releasing the capsule, it was redirected into a solar orbit. Though its mission is over and its systems are likely dead, it continues to drift around the Sun, locked in a lonely path similar to Earth's. Trajectory models suggest it could remain there for centuries. Genesis left behind two ghosts: the shattered crater in the Utah desert and the silent spacecraft bus drifting in space. These remnants serve as a physical archive of the mission. The failure led to changes in parachute design and sensor verification protocols, saving future missions from similar fates. For the scientists who had spent years planning the mission, the crash was a personal loss, seeing their delicate work destroyed in an instant. Yet, the data that survived became even more precious, proving that knowledge can be recovered even from disaster. Scientists treated each recovered particle as something rescued rather than simply delivered. In the lab, researchers continue to study these tiny fragments today. While the sample returned, the original bus of Genesis remains in space. It orbits the Sun, still out there somewhere in the solar wind it was once meant to sample, circling the star that gave it its name. While some spacecraft drift around the Sun, others find their final resting place closer to home. Thousands of satellites orbit Earth. Some are active, sending back data or relaying signals. But many have gone silent. Their fuel ran out, their electronics failed, or their missions ended. Most remain in orbit, drifting. However, not all are left to fall wherever they may. Some are carefully guided to a specific zone, a place sometimes called the graveyard orbit. The graveyard orbit is not a single location, but a band of space situated just above the geostationary belt. This region, roughly 300 kilometers above standard geostationary orbit, is where dead satellites are pushed when their work is done. Geostationary orbit itself is a unique ring located about 35,786 kilometers above the equator. At this altitude, a satellite's orbital speed matches Earth's rotation, making it appear to hang motionless in the sky. This is ideal for communications, weather forecasting, and television broadcasts, as ground dishes can point to a single spot without needing to track movement. But space in this prime belt is limited. Each satellite must stay in its assigned slot to avoid signal interference. With more than 400 active satellites and new launches every year, managing traffic is critical. This is where the graveyard orbit becomes essential. When a geostationary satellite nears the end of its life, operators use its last reserves of fuel to fire thrusters, lifting it out of the active belt and into this higher, quieter zone. Once there, it is out of the way, unlikely to drift back down or interfere with operational spacecraft. This final maneuver is a last act of service. Not all satellites make it. If contact is lost early or fuel runs out unexpectedly, a satellite might become stranded in the main belt, drifting and tumbling uncontrolled. These abandoned objects become hazardous space debris. However, when procedures are followed, the graveyard orbit serves as a quiet repository. Guidelines set by the International Telecommunication Union and other agencies advise lifting satellites at least 300 kilometers above the geostationary ring. Once there, operators must vent remaining fuel to prevent explosions, discharge batteries, lock moving parts, and turn off antennas. The satellite is completely powered down and left alone. Hundreds of satellites now drift in this graveyard. Many have been there for decades cold, inert, and lifeless. Some are relics from the early days of global communication. Others were military surveillance platforms. Now, they serve no purpose except to stay out of the way. Unlike probes sent to the outer planets, these satellites remain tethered to Earth's gravity. They move in large circular paths above the equator, but without active control. Their orbits slowly shift due to the gravitational pull of the Sun, the Moon, and Earth's uneven mass. Some wobble or rotate unpredictably, but without fuel or gyroscopes. They cannot correct themselves. Collisions in this region are rare but possible, with hundreds of objects and more arriving. The zone is becoming crowded. Fortunately, the relative speeds between objects here are low compared to lower orbits, reducing the energy of any potential impact. However, a collision could create debris that threatens other paths. Compared to the crowded highways of low Earth orbit, the graveyard remains a stable, predictable zone far from atmospheric drag. Some residents of this graveyard were once famous names like GOES, Intelsat, or Eutelsat that appeared in news reports. They linked continents and provided real-time weather data. Now, they are silent shells. Their solar arrays float without guidance, paint peels, insulation degrades, and micrometeoroids scar their surfaces. They age in a vacuum, with no air or weather to wear them down. Yet time leaves its mark. There is no plan for recovery. The graveyard orbit is too high for retrieval missions, and these satellites were never designed to return. They will remain there for centuries, perhaps millennia. This ring of shadows is a reminder of the permanence of our presence in space. Long after a mission ends, the physical craft remains, obeying physics, but no longer serving human needs. In low Earth orbit, dead satellites burn up or are deorbited into oceans. But high above, there is no easy return. Moving upward is the safest choice, a kind of space etiquette agreed upon by necessity to keep the vital geostationary belt usable. From the ground, these dead satellites are invisible, but from above, they would appear as a silent crowd, drifting just beyond the edge of activity, far beyond Earth. Another machine rests in silence on an alien moon. On January 14th, 2005, a small spacecraft parachuted through the thick golden clouds of Saturn's largest moon, Titan. It drifted downward for hours, scanning a world no one had ever seen up close. This was Huygens, the first and only visitor to the surface of Titan. The Huygens probe was part of the Cassini-Huygens mission, a collaboration between NASA, the European Space Agency, and the Italian Space Agency. While the larger Cassini orbiter circled Saturn, Huygens was built to detach and fall to Titan. The moon had long been a mystery, wrapped in an orange haze that hid its surface. Astronomers knew it was cold and possessed a thick atmosphere, possibly hosting lakes of liquid methane or ethane. As Huygens descended, it passed through the dense alien air. For 2.5 hours, it floated down, capturing the first photos from within Titan's atmosphere. One image showed a vast, hilly landscape with dark branching lines resembling riverbeds. Another revealed a smooth, rock-strewn surface. The probe sampled the air, finding nitrogen as the primary gas, just like Earth, but mixed with methane. Huygens did not splash down in a sea, as some had speculated. Instead, it landed on solid ground with the consistency of wet sand. For a short time after landing, it continued to send data. The surface temperature was around -179 degrees Celsius. The rocks scattered nearby were likely water ice, frozen as hard as stone, coated in a dark organic soot that had drifted down like snow over millions of years. The probe survived for just over an hour on the surface before its batteries failed. Its mission was to land, work briefly, and then go silent. It did exactly that. Now, Huygens sits alone on Titan, near the moon's equator. It is surrounded by a frozen landscape shaped by methane rain and hydrocarbon clouds. Over time, wind may cover it with fine particles, but in the deep cold, it remains preserved. There is no rust or decay as we know it. Huygens proved that Titan is a complex world with weather, chemistry, and geological activity. It showed us a place where liquid flows, seasons change, and the landscape evolves. Although it found no life, it revealed a world that challenges our understanding of planetary environments. Future missions like the Dragonfly rotorcraft plan to return to Titan. Building on the legacy, Huygens left behind a lonely monument sitting silently in the dark. Before Huygens, Europe had already begun making its mark in deep space. In the 1980s, the European Space Agency launched Giotto, one of its earliest and most ambitious missions. Its target was Halley's Comet, launched in 1985. Giotto was designed to intercept the famous comet during its rare pass through the inner solar system. It was Europe's first deep space mission to encounter a celestial body. The spacecraft was a small, squat cylinder protected by a shield, as approaching a comet meant flying through a cloud of dust and gas at high speed. On March 13th, 1986, Giotto made its closest approach. Coming within 596 kilometers of the comet's nucleus, it sent back the first clear images of a comet core, revealing a dark, rugged object spewing jets of gas, a stark contrast to the bright, icy ball many had imagined. During the encounter, a dust particle struck the spacecraft, knocking it spinning and damaging its camera. However, engineers regained control. Giotto was not finished. Years later, in 1992, it completed a second flyby of Comet Grigg-Schellerup. Since then, it has remained in solar orbit, a silent pioneer that proved Europe could explore beyond Earth. Another early ESA mission was Ulysses, launched in 1990. Although a collaboration with NASA, its operations were largely managed by Europe. Ulysses was built to study the sun, not by looking at it directly from the equatorial plane, but by flying over its poles. To achieve this, the spacecraft took a long and unusual route, using Jupiter's massive gravity to slingshot itself out of the plane of the solar system. Once in its final orbit, Ulysses circled the sun at a steep angle, passing over the north and south poles. It carried instruments to measure the solar wind, magnetic fields, and cosmic particles in regions no spacecraft had ever visited. It operated far longer than expected, more than 18 years, before finally losing power in 2009. Now, it is another silent traveler, drifting on a unique path far from the plane where most planets orbit. There were other missions too. The Infrared Space Observatory, launched in 1995, did not travel as far but left a significant mark. Herschel and Planck followed years later, giving Europe a strong presence in space-based astronomy. These observatories didn't explore planets or comets, but instead looked at the universe itself, its cold dust, distant galaxies, and the faint glow of the Big Bang. Smart 1, launched in 2003, was a testbed for solar electric propulsion. It went to the moon, circled it for months, and was then deliberately crashed into the surface. It proved that European-built spacecraft could reach beyond Earth and perform long-term science using advanced propulsion. This paved the way for more ambitious projects like Rosetta. Although separated by decades, Giotto and Rosetta were linked by shared goals, shared risks, and a European desire to explore objects up close. These early ESA missions were often smaller and built on tighter budgets than their American counterparts. But they were ambitious in their own way. They marked Europe's shift from launching weather satellites to flying deep into the solar system. Occasionally, Mission Control might point a dish at the sky, hoping to catch a faint signal from these old travelers. In rare cases, it has happened. In 2008, ESA tracked Giotto again for a short time, confirming it was still tumbling through space, but the spacecraft did not respond. The silence confirmed what was already known. It was there, but it had nothing more to say. In time, new missions will follow. Europe continues to build spacecraft that reach far beyond Earth, like the Jupiter Icy Moons Explorer, JUICE, launched to study the Jovian system. But the first steps were taken by small, simple probes like Giotto and Ulysses. They proved it could be done and earned their place in the silent fleet that now drifts between the stars. While ESA explored from a distance, another mission decided to make physical contact. NASA's Deep Impact Probe traveled over 130 million kilometers to reach Comet Tempel 1. When it arrived, it released a copper-filled impactor, essentially a bullet, and steered it directly into the comet's surface at over 10 kilometers per second. The resulting collision kicked up a cloud of dust and gas that glowed in sunlight, forming a temporary halo around the comet. For the first time, scientists could see inside a comet by forcefully opening it up. The mission had two main components: the flyby spacecraft and the impactor. The flyby craft carried cameras, sensors, and a high-gain antenna, watching from a safe distance, while the impactor, about the size of a small desk, took the plunge. The impactor's goal was simple: slam into the surface, survive long enough to send back close-up images, and then be obliterated. It performed exactly as planned. In its final moments, the impactor transmitted detailed pictures of the comet's surface, revealing a rough, shadowy terrain pocked with ridges and slopes. Then the images stopped. A bright flash followed, captured by the flyby craft. Marking the instant the impactor vaporized into a burst of ice and dust, the flyby craft trained its instruments on the plume. Analyzing the dust particles and gas composition, scientists learned that the interior of the comet was made of fine, powdery material containing water, carbon dioxide, and complex organics, the raw ingredients of the solar system. But the impact had another consequence. It left behind a crater that the Deep Impact spacecraft itself never saw in detail. The cloud of debris was so dense and the flyby so fast that the spacecraft couldn't see through the plume to the hole it had created. For years, the exact aftermath remained unknown. It wasn't until 2011 that NASA's Stardust XT spacecraft flew by Comet Tempel 1 again. It spotted a shallow depression where the impactor had hit. The crater was about 150 meters wide and 20 meters deep, less dramatic than some expected, but clearly visible. The wound in the comet's surface marked the place where humanity had reached out and physically reshaped a celestial body. After the main event, the Deep Impact flyby spacecraft remained functional. Instead of retiring it, NASA gave it more work, renamed EPOXY. The spacecraft was reprogrammed to study extrasolar planets and revisit another comet. In 2010, it encountered Comet Hartley 2, a smaller, hyperactive body spewing jets of carbon dioxide. The images revealed a peanut-shaped object with one end covered in icy particles and the other relatively quiet, designed for a short mission. The spacecraft had now been operating for years longer than planned. Its systems were degrading. In August 2013, contact was lost. The last signal indicated the spacecraft had lost track of its orientation due to a computer timing error. Unable to point its solar panels toward the sun, it likely ran out of power and went silent. The debris cloud from its impact on Tempel 1 is still out there, stretched thin by solar radiation. The flyby spacecraft itself is now in a stable heliocentric orbit, circling the sun once every 1.5 years, a broken eye drifting in the dark. While Deep Impact succeeded, another ambitious mission failed before it could truly begin. In the quiet hours of a November night in 2011, a Russian rocket climbed into the sky carrying Phobos Grunt, a probe meant to revive a nation's legacy in deep space, named after its destination. Phobos, the larger of Mars's 2 moons, and Grunt, the Russian word for soil. The mission's goal was to bring back a sample of the moon's surface. It would have been Russia's first interplanetary sample return mission, a defining moment that could place the country back at the forefront of Mars exploration. Phobos Grunt launched atop a Zenit rocket from the Baikonur Cosmodrome. The launch went well, and the spacecraft entered low Earth orbit. The upper stage, known as the Fregat Propulsion Module, was supposed to ignite and send the probe toward Mars. It never did. The spacecraft remained stranded in Earth orbit. Mission controllers tried repeatedly to wake the upper stage, but no response came. The probe had power and its solar panels were deployed, but it was going nowhere. Engineers never fully confirmed the root cause, but theories ranged from software faults caused by radiation to hurried development cycles and aging hardware. The failure was a significant blow. Phobos Grunt was not just a Russian project. It carried a small Chinese orbiter, called Yinghuo 1, which was intended to be China's first Mars probe. That ambition fell with the main spacecraft. Also on board were biological experiments, including microbes and tiny crustaceans, meant to test survival in deep space. Like the rest of the payload, they never left Earth's grasp. For weeks, the stranded spacecraft circled Earth, slowly losing altitude due to atmospheric drag. On January 15th, 2012, Phobos Grunt re-entered the atmosphere over the Pacific Ocean. Most of it burned up, though debris may have splashed into the sea. This failure echoed the past. In 1988, the Soviet Union had lost Phobos 1 and Phobos 2, one en route and the other just before deploying landers. Phobos Grunt became a cautionary tale of the risks in planetary science. It left behind no scientific data, only a legacy of what might have been. The hardware is gone, scattered across the ocean floor or vaporized in the upper atmosphere. What remains are blueprints in archives and the memory of a bold attempt to reach a Martian moon that ended before it could leave home, while Phobos Grunt fell silent. Another mission from a different nation managed to reach the Red Planet and exceed all expectations. This was the Mars Orbiter mission. Launched by the Indian Space Research Organization, ISRO, in November 2013 at the Satish Dhawan Space Center. A rocket lifted off carrying India's first interplanetary spacecraft. The name of the mission was straightforward: the Mars Orbiter Mission, or MOM. This was India's first attempt to reach another planet. A newcomer to deep space exploration, the Indian Space Research Organization, ISRO, was stepping into a field dominated by giants like NASA, Roscosmos, and the European Space Agency. Yet, it made history. MOM was built on a modest budget. Reports often compared its cost to that of a Hollywood movie, around $74 million. This figure covered a full planetary mission, including launch, transfer, orbital insertion, and science operations. MOM was designed, built, and launched within a span of less than 2 years. That speed, combined with its frugal nature, earned it both admiration and skepticism. The spacecraft launched aboard a PSLV-XL rocket, the most powerful version of India's workhorse launcher. Since the PSLV could not send MOM directly to Mars, the spacecraft first performed a series of complex maneuvers around Earth. It executed apogee-raising burns, firing its engines at precise moments to stretch its orbit higher and higher until it finally broke free from Earth's gravity and began its 300-day journey to the Red Planet. MOM arrived at Mars in September 2014. As the spacecraft approached its target, tension filled the ISRO control room. One critical maneuver remained: Mars orbit insertion. If the main engine failed to fire, or if the spacecraft turned the wrong way, the probe would sail past Mars forever, lost in a heliocentric orbit. But the maneuver went smoothly. The engine fired for the required duration, slowing MOM down enough to fall into orbit. India had achieved what no other country had done on its first attempt: a successful Mars mission. Even the United States and the Soviet Union had required multiple tries to get it right. MOM carried 5 scientific instruments, including a color camera to image the surface, and a methane sensor to search for signs of biological or geological activity. Its science goals were modest compared to larger missions, but its true value lay in proving that a newer space power could achieve the impossible. For years, Mom took images and relayed data back to Earth. It captured shots of the Martian disk with polar caps visible, cloud formations over ancient craters, and surface details seen from afar. Designed to last only 6 months, the spacecraft remained active for several years. Engineers adjusted its orbit to extend its life, tweaking its position as the Martian seasons changed. By 2020, it had long outlived expectations. Then, in 2022, contact was lost. ISRO officials later explained that the spacecraft had likely run out of fuel. Without propellant, it could no longer maintain its orientation toward Earth and the Sun. The solar panels stopped generating power, and Mom went silent. There were no final messages or emergency beacons. Even now, Mom likely remains in orbit, a dark and unresponsive companion to other derelict spacecraft circling the planet. It stands as the only Martian orbiter from a nation that had never been there before, a quiet signal of a new spacefaring country finding its place among the stars. Mom demonstrated that Mars was no longer off limits to newcomers. With careful planning and resource management, reaching another planet was possible without a decades-old deep space program. It reshaped the narrative of exploration, showing that new voices are joining the chorus to expand our understanding of the solar system. While nations launch missions like MOM, another class of spacecraft has begun to populate the void, the tiny ghosts known as CubeSats. Born from university labs in the early 2000s, CubeSats started as small, box-shaped devices measuring just 10 centimeters on a side. They were secondary payloads, hitching rides with larger missions to test hardware or collect basic data. But over the next 2 decades, they evolved. Some left Earth entirely, aiming for the Moon, Mars, and beyond. CubeSats are not built like traditional probes. Their design is simple, modular, and limited by size. A single unit, or 1U, weighs around a kilogram. Larger versions, like 6U, offer more capability but are still dwarfed by conventional spacecraft. Once a CubeSat leaves Earth, it faces the same radiation and thermal extremes as a probe the size of a car. One of the first to stretch these boundaries was MARCO, short for Mars Cube 1. These twin 6U CubeSats, nicknamed Eve and Wally, launched alongside NASA's InSight lander in 2018. Their purpose was to relay data from InSight during its descent to the Martian surface. It was a test to see if small satellites could survive the journey to Mars. They succeeded, relaying signals in real time as InSight touched down. After flying past Mars, both units continued into heliocentric orbit, lacking propulsion to adjust course. They eventually drifted too far for their limited communication systems. Wally went silent first, followed by Eve. Other missions followed. When NASA's Artemis 1 launched in 2022, it carried 10 CubeSats designed for lunar and deep space tasks. Among them were Luna HMAP, intended to map hydrogen at the lunar South Pole, and Omotenashi, a Japanese attempt to land a tiny probe on the Moon. However, deep space is unforgiving. Omotenashi failed to communicate after deployment, and never received the commands to land. Luna HMAP suffered a propulsion failure and could not enter lunar orbit. Both drifted away, joining the ranks of lost microsatellites. CubeSats are vulnerable. A software glitch or hardware failure manageable on a large spacecraft can be fatal to a CubeSat, which often lacks backup systems. Yet, their low cost and fast development cycles make them appealing. They allow students, startups, and small teams to attempt missions that were once impossible. Each silent CubeSat defines the limits of what works and what fails, informing the next generation of designs. As the field matures, more of these tiny explorers will venture out. Some will orbit the moon, others may follow missions to asteroids. Each carries the lessons of those that came before the silent cubes, now drifting unseen between planets, long before CubeSats. A much larger but equally silent observer circled the moon. In the early 1970s, NASA launched Explorer 49, a strange spacecraft designed not to look, but to listen. Launched on June 10th, 1973. Explorer 49 was a radio astronomy mission. Unlike orbiters carrying cameras, it sought the quietest place near Earth, the far side of the moon. Earth is a noisy planet for radio astronomy. With its atmosphere and human-made signals cluttering the air, the moon acts as a massive shield, blocking this interference. By positioning itself behind the moon, Explorer 49 could listen to the universe in peace. To catch faint radio waves, the spacecraft needed enormous antennas. Once in lunar orbit, it extended 4 flexible booms, forming a giant X shape that spanned 229 meters from tip to tip. This made it, effectively, the largest structure ever deployed in space at the time. These thin, wire-like arms allowed Explorer 49 to map the sky in low-frequency radio waves, signals that are blocked by Earth's atmosphere. These frequencies carry whispers from the oldest and most mysterious objects in the universe: pulsars, quasars, and the cosmic background radiation. For 2 years, Explorer 49 circled the moon in a highly elliptical orbit, gathering data on this invisible universe. Radio waves do not create sharp pictures. They form noisy maps full of static. Yet, even these fuzzy outlines revealed patterns about galactic radio emissions and magnetic fields in deep space. By 1975, communications ended. The spacecraft had completed its work. The long antennas, once precise listening devices, became dead weight. Orbital calculations suggest the spacecraft eventually crashed into the lunar surface. Explorer 49 remains a unique chapter in space history, a pure science mission with no rovers or photos. Just data gathered in a pocket of silence found only behind the moon. It was a proof of concept that listening from lunar orbit was possible, expanding our reach into frequencies never before mapped. Today, new proposals still refer to Explorer 49 when discussing the benefits of far-side astronomy. It stands as an example of how science doesn't always need big spectacles. The antennas it carried stretched out like ghostly threads, measuring signals from beyond the galaxy. In an age of moon boots and Mars landers, Explorer 49 was quiet. It looked past the local and focused on the cosmic, while Explorer 49 listened to the deep universe. Another spacecraft set its sights on a specific, elusive target. Mariner 4 was the first to show the world what Mars actually looked like. It was the moment humanity truly saw the red planet up close. Launched on November 28, 1964, by NASA. Mariner 4 was part of the larger Mariner program, small by today's standards, with a mass of less than 300 kilograms. It was powered by solar panels and a modest antenna. Its mission was to fly by Mars, gather scientific data, and take photographs as it swept past. Previous attempts by both the United States and the Soviet Union had failed. Mars was proving a difficult target, far more challenging than Earth's moon or nearby Venus. Getting there required precise timing, powerful boosters, and equipment that could survive the deep cold of interplanetary space. Once launched, Mariner 4 began a long cruise phase. It drifted across space for over 7 months before finally reaching its closest approach on July 14th, 1965. As it neared the planet, its instruments came to life. The most important among them was its television camera. A simple imaging system by modern standards, it took 21 images in total, using a slow scanning process to capture black and white pictures line by line. Storing them on a small onboard tape recorder, these images were later sent back to Earth at a pace so slow that the process took weeks. But when the first ones arrived, the world watched closely. Mars, long thought of as potentially Earth-like, appeared barren and harsh instead of oceans or green valleys. The images showed a cratered surface, dry and dusty, more like the moon than a second Earth. There were no signs of canals, no signs of life, and no clear evidence of atmosphere or water. For a public raised on science fiction, it was a sobering view, but for scientists, it was a huge step forward. These were the first direct observations, setting the stage for everything that followed. Mariner 4 also collected data on Mars's atmosphere and magnetic field. It found that the atmosphere was incredibly thin, mostly carbon dioxide, and less than 1% of Earth's surface pressure. It also detected no significant magnetic field, suggesting that Mars lacked the internal dynamo that protects Earth from solar radiation. Once the flyby was complete, Mariner 4 continued on its path. Still functional, it drifted into a long heliocentric orbit around the Sun, lacking propulsion to adjust its course. It simply became another object moving through space. It passed through conjunction with the Sun, temporarily losing communication as it moved behind the star. After contact was reestablished, engineers decided to keep using the spacecraft. For nearly 3 more years, Mariner 4 provided data on the space environment, including cosmic rays and solar wind. Eventually, instruments wore out, the tape recorder failed, and power levels dropped. In late 1967, contact was officially lost. Today, Mariner 4 orbits the Sun once every 20 months or so. Its path carries it both closer to the Sun and farther away. Stretching beyond Mars's orbit, it poses no collision risk and has no active systems. It is just drifting a silent witness to a past era. It is easy to forget how primitive spaceflight was in those early years. Mariner 4's camera system operated on instructions programmed using punch card logic. At one point, when data was coming back slower than expected, NASA engineers took raw numbers from the spacecraft and used colored pencils to hand draw the first picture. Even without the final photo, they wanted to glimpse what was waiting on the other side. That sketch, the first image of Mars ever seen by human hands, was grainy and crude, but meaningful. Mariner 4 proved that a machine could travel to another world and bring back real knowledge. If someone were ever to find it in the distant future, they might see its weathered metal and dark solar panels and recognize it for what it was, a machine that carried a glimpse across space, forever changing what we imagined was possible. The technology powering these early missions was incredibly basic compared to modern standards. The computers used in early space probes were never meant to match Earth-based systems. They were built to be reliable, durable, and energy efficient. They had to survive launch stress, the vacuum of space, and decades of cold and radiation. Most importantly, these machines were tailored to specific missions. Code was written by hand and loaded before launch, rarely changed afterward. The software was minimal, and the hardware was basic. But they worked. For example, the Voyager spacecraft each carried 3 separate computer systems, one for commands, one for flight data, and one for attitude control. The processors inside these systems had word lengths of 18 bits and operated at speeds barely noticeable today. Total memory on board was just under 70 kilobytes less than the size of a single modern photo. These computers didn't even use silicon chips in the way we think of them now. Much of the memory was made using magnetic cores, tiny loops of wire wrapped around magnetic material. Data was stored by magnetizing the cores in a specific direction. It was technology chosen for stability, not speed. It was non-volatile and resistant to radiation. These machines were designed to last, and they did. Voyager 1 and 2 are still communicating with Earth. They're ancient computers still executing sequences and processing data. In recent years, engineers have had to rewrite software routines to bypass failing hardware sections, keeping these aging machines alive far beyond their expected limits. Pioneer 10 and 11 also carried modest onboard computers. Pioneer 10's command system could store only 5 commands at a time, queued up from Earth. There was no autonomy. If a problem occurred while out of contact, the spacecraft couldn't correct itself. Yet, Pioneer 10 operated for more than 30 years. What connects all these spacecraft is the simplicity of their design. In many ways, their computers resemble those found in early personal computers, like the TRS-80 or Apple II small memory. Slow processing and text-only interfaces. But they offered predictability. They were systems that didn't crash without reason. They executed steps exactly as told, which made them perfect for space, where repairs are impossible. Engineers could test every line of code because there were no massive operating systems or third-party software. Of course, limits existed. Low memory meant science data had to be compressed. Low speeds meant high-resolution images took hours to transmit. Commands had to be flawless. As time passed, newer spacecraft adopted more modern systems. Galileo used processors based on the RCA 1802 chip, and later missions like Cassini used radiation-hardened PowerPC chips. But even today, space missions often use hardware that is years behind consumer technology because stability matters more than speed. If these old computers were ever found by future explorers, they would be like digital fossils. Inside their circuits, frozen in time, are the ideas of the people who sent them. They may not be powerful, but they have traveled farther than any other human-made object, outliving their designers and proving that sometimes simple and steady is enough. However, the legacy of these past missions isn't just in deep space. Closer to home, the remnants of our history are becoming a problem. Do ghost satellites interfere with space exploration today? The answer is increasingly yes. Space exploration depends on carefully mapped orbits. Every working satellite must navigate regions crowded with objects, both alive and dead. Defunct machines can cause damage and force active missions to make emergency maneuvers. Most ghost satellites come from earlier eras when disposal wasn't a priority. In low Earth orbit, atmospheric drag eventually cleans up debris. But in higher orbits like medium Earth orbit or geostationary orbit, satellites can remain practically forever. In 2009, the risk became real. An active Iridium communications satellite collided with a defunct Russian satellite. Cosmos 2251. The two slammed into each other at over 41,000 kilometers per hour. Both were destroyed, creating more than 2,000 trackable pieces of debris. This was a wake-up call. It proved that ghost satellites are hazards. Space agencies now track thousands of defunct objects. The U.S. Space Surveillance Network catalogs more than 25,000 items, but many more are too small to see. These include paint flecks, bolts, and fragments from explosions. Together, they form a cloud of space junk. The biggest concern isn't always large satellites, which are easy to track, but the smaller, fast-moving fragments. Active spacecraft often have to perform collision avoidance maneuvers. This uses fuel, time, and resources. The International Space Station has changed its orbit multiple times to dodge debris. Every maneuver disrupts schedules and experiments. In geostationary orbit, operators are now expected to move satellites to a graveyard orbit at the end of their lives. But older satellites abandoned before these protocols remain as motionless sentinels. Modern mission planners must account for them. Before launch, teams simulate thousands of trajectories to avoid known hazards. Collision risks can be identified just hours before a close pass, requiring quick calculations. Governments and private companies are discussing solutions, including active removal missions using robotic craft, nets, harpoons, or lasers. Some research teams are developing tow trucks to drag dead satellites into the atmosphere. But these solutions are complex, expensive, and politically sensitive. For now, the ghosts remain, drifting in the dark, forcing us to watch our step as we continue to climb into the sky. A satellite removal craft, designed to grapple and move dead objects, can look very similar to an anti-satellite weapon, slowing international cooperation on cleanup efforts. In low Earth orbit, the rise of mega-constellations like SpaceX's Starlink adds another layer of concern. These networks involve thousands of satellites launched in tight formations, though most are active and maneuverable. Even a small percentage of failures could create long-term risks if the dead units cannot be deorbited. Ghost satellites passing through these orbital shells could trigger cascading collisions, a feared scenario known as the Kessler syndrome, where debris creates more debris in an unstoppable chain reaction. For now, most ghost satellites in geostationary orbit are not causing daily disruptions. They remain background risks known, but passive. However, the population is growing. Each new launch adds to the crowd, and not every mission ends with a clean disposal. Some of these derelicts are still studied for research. Their orbits help test tracking software, and their surfaces offer insights into space weathering, micrometeoroid impacts, and radiation exposure. A few are even used as targets for ground-based laser communication tests. But none of this changes the basic truth. They are inactive, and they are in the way. In the decades ahead, managing this debris will become a priority. Nations are already creating guidelines for space traffic management, similar to air traffic control. But unlike airplanes, most satellites cannot be steered once they die. Each one represents a lesson in persistence, shaping the decisions of every new mission that follows. This raises a crucial question. Who keeps track of the forgotten ones? Keeping tabs on inactive spacecraft and debris requires powerful radar, precise mathematical models, and international coordination. But for spacecraft that travel far beyond Earth into deep space, tracking becomes significantly harder. Even the agencies that launch them eventually lose their grasp on exactly where they are. The responsibility to track these distant travelers falls to a small number of specialized systems. The most important is the Deep Space Network, or DSN, operated by NASA. The DSN is a global system of massive radio antennas capable of communicating with spacecraft millions or even billions of kilometers away. The network consists of 3 main sites: Goldstone in California, Madrid in Spain, and Canberra in Australia. These locations are spaced evenly around the globe so that as the Earth rotates, at least one station can always maintain a line of sight with any spacecraft in the sky. The DSN was built to support active missions. It guides spacecraft during planetary flybys, collects data during landings, and captures scientific discoveries. But once a mission ends, once the spacecraft is shut off or fails, the need for constant contact disappears. That is when these machines become harder to follow. Some old spacecraft remain easy to track because they follow predictable orbits. Even without communication, scientists can estimate their location using their last known velocity and position. Gravitational models help predict their paths. However, the longer a spacecraft has been inactive, the more uncertain those predictions become. A small change in velocity, caused by something as simple as a gas leak or the pressure of sunlight, can alter an orbit. In deep space, even a tiny shift can become a large error over time. If a spacecraft has gone completely dark, tracking it depends entirely on ground-based radar or optical telescopes. In Earth's orbit, systems like the U.S. Space Surveillance Network can track objects as small as a softball. But in deep space, radar becomes much less effective. The distances are simply too vast. The signal strength needed to bounce a radar pulse off a small probe near Jupiter and receive an echo would be enormous. Most defunct spacecraft are too small and too far away to reflect a detectable signal. Some nations maintain lists of known space objects. The United States keeps a public catalog through entities like US Space Command. Russia and China maintain similar databases. However, these catalogs focus mostly on Earth orbit. When it comes to deep space, many objects are simply marked as lost contact or status unknown. There are growing efforts in the private sector to improve tracking. Companies like Leo Labs and Astroscale use networks of ground-based sensors to watch for debris. However, these efforts also focus mainly on near-Earth space, particularly low Earth orbit and geostationary orbit, where commercial traffic operates. Very few private entities track anything in interplanetary space when an old spacecraft like Voyager 1 or Voyager 2 is still active. It remains part of the DSN's regular schedule. But even for these legends, time is limited. The DSN serves many missions at once, and antenna time is precious. Engineers must carefully schedule when each dish points at a specific target. For the Voyagers, contact windows are now limited to just a few hours a day, and the signals they send are incredibly weak. When contact is lost completely, some spacecraft are intentionally forgotten. Mission teams may try for weeks or months to re-establish a signal. If no response comes, the mission is declared over. But declaring a mission over doesn't mean the spacecraft vanishes. It just means we have stopped listening. In rare cases, decades later, a signal might be rediscovered. This happened with NASA's IMAGE satellite, which went dark in 2005, only to be unexpectedly found transmitting again in 2018 by an amateur radio operator. Engineers scrambled to reconnect, and for a short time, the satellite came back to life before going quiet once more. Most spacecraft are not so lucky. They go silent and stay silent. While their physical presence continues, they no longer receive attention. The DSN does not waste time scanning the sky for ghosts. It focuses on missions with goals, instruments, and working transmitters. That leaves many old probes drifting in silence. How much effort should be made to track something that no longer functions? The data collected by these missions has already shaped our understanding. Their value was in the information they provided while alive. Now, their bodies remain out there, space debris to some, historical monuments to others. Even when untracked, they remain in motion. Some follow heliocentric orbits, circling the sun like tiny, artificial planets. Others are on escape trajectories, pulled ever farther from the sun, beyond the influence of the solar system. These are the most unreachable of all. For all practical purposes, they are lost to us. The Deep Space Network and its partners track the living missions, guide them through the dark, and listen to their last signals. Sometimes those signals come just before a planned shutdown, a final whisper, a data dump, a goodbye from a craft that knows its time is done. The DSN logs it, stores it, marks the mission as ended, and then the antennas turn to the next target. But even then, somewhere in the archives, the name remains. The last known coordinates, the orbital path, the frequency it once used to trace in the records, proving that this machine existed and that someone once cared where it was. In that quiet bit of bookkeeping, the forgotten ones are remembered after all.